Okay, let's unpack this. We are diving headfirst into this paradox that I think keeps every security team and frankly every operations team awake at night.
It really does. It's this constant tension.
Right, you're forced to update all the time to patch these critical vulnerabilities, but at the same time, every catch cycle feels like you're just, I don't know, rolling the dice on a guaranteed outage.
It feels like a guaranteed path to some kind of operational catastrophe. You know,
Yeah.
patching is going to break something, and downtime is just, it's not just money anymore. It's your reputation on the line.
It's the ultimate high-stakes dilemma, isn't it? You have to move at the speed of the threats, which is, well, basically instant.
Lightning fast, but your systems, your processes for actually verifying a patch and rolling it back if something goes wrong, they move at a glacial pace.
And that friction is where all the risk lives.
Exactly. So for you, our listener, the learner, what we're trying to do here is build a coherent strategy to get rid of that tension. And we've gathered sources that really provide that blueprint.
A blueprint that bridges the gap from kind of timeless security theory all the way up to the really cutting-edge stuff.
All the way to cryptographically enforced cloud deployment and, modern access controls.
Absolutely. So our mission today is to give you a true shortcut. It's a comprehensive look at 3 interconnected pillars of modern system security.
Okay, let's lay them out.
First, we're setting the bedrock. We're talking foundational server security, straight from the guidance at NIST. No skipping the fundamentals.
Then we jump into what I'd call radical operational resilience. We're talking blue-green deployment.
A technique that can turn, hours of catastrophic rollback into something that's less than 30 seconds, a near non-event.
It's a game changer. And then third, we're leaping into the future of trust. How do we build and use explicit, verifiable digital evidence?
Attestations.
Attestations, exactly. And combine that with next-generation access models like multi-root trustless access.
So our stack of sources today is pretty powerful. We have the essential NIST guidelines for governance.
We have a complete phase-by-phase blueprint for doing those instant rollbacks.
And a really deep, actionable look at modern shifting left techniques, binary authorization.
And these trustless access models that are designed from the ground up to eliminate single points of failure, whether that's a human or a machine.
Yeah.
We're charting a whole journey, really.
From that old school data center mentality to, I guess, the decentralized, multi-cloud, cryptographic future.
That's the path.
All right, let's start where every security discussion really has to begin, the foundation. When we talk about servers, and it doesn't matter if they're physical, virtual, or in a container, what is it that makes them such a high-value target?
Well, it's their function, right? A server is a host that exists to provide services over a network. That's its primary continuous job.
So it's not like a laptop that goes to sleep. It's always on, always accessible.
Always on, always accessible, and always providing a service. Think email, databases, web content. And because they're designed that way, they present a constant, very high visibility target for attackers.
And if an attacker manages to breach that host, what are they trying to do? What are the main goals?
There are 4 core goals, really, that map to the threats they face. The most classic one is just exploiting a software bug.
A remote code execution?
Exactly. Get unauthorized access. The second is the denial of service attack, the DOS attack. Basically, just make the service unavailable to the people who need it.
Okay, so that's an attack on availability. But what about the data itself?
That's goals 3 and 4. They want to read or change sensitive information. We're talking PII, credit card data, intellectual property. That's a violation of both confidentiality and integrity.
And then there's the one that really keeps admins up at night.
The most insidious one, yes. Using your compromised server as a launchpad. Because servers usually sit in these high-trust network zones, an attacker can use them to pivot and attack other internal systems.
Or serve malware to your customers.
Or serve malware, absolutely. They become these incredibly high-leverage assets for an attacker.
So it sounds like we're constantly juggling 3 different objectives, which of course brings us to the famous CIA triad.
Confidentiality, integrity, and availability.
Yeah, it's the bedrock of any security system.
Non-negotiable. Confidentiality is about access control. Who can read what? Integrity is about making sure the data is authentic and hasn't been tampered with.
And availability is the operational side of things. Can your legitimate users actually get to the information when they need to?
Precisely. And NIST, specifically FIPS Pub 199, gives us the framework for classifying the impact if we fail on any of those 3.
So you get low, moderate, or high impact levels.
Right. And that classification dictates everything. It tells you how many resources, what kind of controls you need to apply. A limited adverse effect is low, significant degradation is moderate.
And severe degradation or loss of mission capability, that's a high protection system.
And the real insight from NIST isn't just about applying controls. It's that you have to start this process with planning, way before you even think about deployment.
That planning stage can feel like just, bureaucratic overhead, but NIST seems to treat it as a critical security measure in itself. Why is it so paramount?
Because the biggest failures, they almost always stem from a lack of foresight, especially around consistency in personnel.
Consistency, meaning every server is configured the same way.
Exactly. You have to develop detailed deployment plans and then strictly standardize your configurations. If you let every admin configure servers in their own unique way, you end up with configuration chaos. And you simply cannot secure chaos.
You mentioned personnel. This is the human resource part that often gets glossed over in these technical deep dives.
The most common point of failure. You can have the best tech in the world, but it's useless if your staff is insufficient or unskilled.
So NIST forces you to actually sit down and think about this.
It forces you to identify the roles you need, admins, network experts, and crucially, the information system security officers, the ISOs. And beyond that, you have to assess the skills they need, the training they require, and make sure you have adequate staffing.
Because if you have one person managing 50 servers,
you're going to have security drift. It's inevitable. They just don't have the time for proper monitoring and maintenance. So your staffing plan is a security control.
That's a great way to put it. Okay, so if the team is overwhelmed, the best tech will just atrophy. Let's talk about that tech. Let's start with securing the operating system itself, the hardening process.
Hardening is absolutely foundational. It's this structured process of configuring the OS to minimize the attack surface. And it almost always means moving away from the easy-to-use manufacturer defaults.
Because the defaults are always optimized for functionality and convenience, right? Not for security.
Never for security. The goal here is consistency. You use standardized configuration guides, checklists to make sure every single server build is repeatable and secure.
And the whole philosophy driving this is the principle of least privilege.
Total minimalism.
What does that mean in practice for a server's day-to-day state?
It means the server should only be running the absolute bare minimum required to do its job. Nothing else. You have to audit and then remove or disable every unnecessary service, application, and network protocol.
Like Telnet, which is just sending things in plain text.
Telnet, NFS, if you're not a file server. Even things that seem harmless, like Bonjour or old wireless networking components, if it exists on the system, an attacker could potentially find a vulnerability in it.
So if you remove it, you remove that entire class of threat.
You just eliminate it. Simple as that.
Okay, so that's slimming down the server's attack surface. What about the people who do need to log in? How do we enforce strong authentication and stop the common attacks?
Well, you have to enforce strict password policies and then have robust prevention methods. For passwords, the NIST guidance is pretty standard, but it's so often ignored.
We're talking minimum length, complexity, not using dictionary words.
And the minimum length guidance is way beyond the old 8-character standard now. But critically, you have to make sure passwords are never, ever stored in an unencrypted format, always salted and hashed.
And what about stopping the brute force attacks, the constant guessing?
The system has to actively fight that. The best way is to exponentially increase the delay between login attempts with each failure.
So the more you fail, the longer you have to wait.
Exactly. It makes automated attacks impractical. If you can't do that, the alternative is account lockouts. After, say, 3 to 5 failed attempts, you lock the account for 30 minutes or until an admin manually intervenes.
That stops the bots in their tracks.
It forces them to move on to easier targets.
So once someone is authenticated, you then use resource controls to limit what they can actually do, to limit the potential damage.
That's right. Resource controls limit access to files, directories, devices, all based on need to know. Denying read access protects confidentiality. Denying write access protects integrity.
Preventing someone from corrupting files or uploading malware.
Right. And you also limit execution privileges for common system tools. That stops an attacker from using a compromised host to pivot and launch more attacks on your network.
A really powerful defense, especially for servers facing the public internet, is this idea of the sandbox defense. Can you explain how running software in a jail fundamentally changes the threat model?
A sandbox or a jail is an OS feature that basically puts a process inside a little virtual bubble. It's a highly constrained environment.
The classic example is root in Unix.
Root is the perfect example. It changes what the application thinks is the root directory of the whole system. The OS is configured so the server process and anything it does is contained. It literally can't see or break out of that virtual boundary.
So if a hacker does exploit a vulnerability in your web server,
they only get access to the very limited virtual file system inside the jail. They can't get to the underlying OS. They can't see the real configuration files. It contains the blast radius to almost nothing.
that's a fundamental layer of protection. But today, most organizations are running heavily virtualized environments. So we have to talk about security at the hypervisor layer, especially for network traffic between VMs.
Right, VM security adds this whole new layer of complexity because a lot of the traffic never even hits a physical wire. It's all internal to the hypervisor host.
So the focus has to be on network protection and segmentation within that virtual world.
Exactly. It's a separate concern from just securing the guest OS inside the VM.
So what are the best ways to do virtual firewalls in that context?
Well, the preference is really moving towards kernel-based virtual firewalls. These run as loadable kernel modules, or LKMs, directly inside the hypervisor's kernel.
And that location gives them some big advantages, I assume.
Two massive ones. First, performance. They're incredibly fast because they're using the hypervisor's direct hardware access. And second, and this is the crucial security part, they have superior low-level visibility into the VM state.
They can see things an application-level firewall running inside the VM could never see.
Never. They see the virtual hardware, the memory, the storage. And the key security benefit is if the VM itself gets compromised.
The firewall is completely out of reach?
Totally out of reach. The rogue VM can't monitor it, can't change its configuration, can't disable it. It's an external security guard, independent of the thing it's protecting. That separation is vital.
Okay, what about network segmentation? Keeping that VM traffic separate. We hear about VLANs all the time. What are their limits in a big cloud environment?
VLANs are the traditional method, and they're decent. They work at the port level on a virtual switch. But the protocol itself has a hard limit.
The 4,000 ID limit.
Right, just over 4,000 unique segments because the VLAN ID field is only 12 bits long. In a massive cloud with tens of thousands of tenants or microservices, you hit that wall very, very quickly.
And it makes moving VMs around a pain, too.
It does. It can lead to really bloated and complex configurations on the physical network. It's brittle.
So how does something like VXLAN solve that problem?
VXLAN, or Virtual Extended Local Area Network, it just flips the model. It creates an overlay network. Think of it like a separate fiber network running under the city, totally independent of the streets on top.
So it encapsulates the VM traffic inside standard IP packets.
Exactly. The logical layer 2 network, which is your VM traffic, gets wrapped up in a standard layer 3 IP UDP packet.
Meaning the physical network underneath doesn't even need to know about the segmentation.
It has no idea. It just sees standard IP traffic. This means your number of segments is now limited by your IP addressing scheme, which is huge.
Yeah.
Not by that fixed 4,000 ID limit.
And that gives you much better mobility for your VMs.
Vastly superior mobility and performance. You can move compute resources anywhere you want based on load, completely independent of the physical network layout. It's really the essential networking tech for any large elastic cloud.
Okay, so that's a really robust foundational layer. We've got a secure OS, strong authentication, sandboxing, modern network segmentation, but we're right back where we started.
Back to the anxiety.
Back to the anxiety. Because all of this careful configuration is at risk the moment a zero-day vulnerability drops and you have to patch production without, setting the business on fire.
And that anxiety is the perfect transition into the next layer of risk management. It's about operations.
If that first section was about minimizing the attack surface with static controls.
This next section is all about dynamic resilience. It's about managing the risk that comes from change itself.
So let's really paint that nightmare scenario for everyone. It's 3 a.m., the phone rings, and we're not talking about a minor bug here. We're talking about a critical high CVSS vulnerability.
Something in the kernel or a core web server component.
Yeah.
The pressure to patch immediately is just immense.
So the team pushes the patch to production, and right away, things start to go sideways.
The system comes back up, but then you find some hidden dependency conflict. That WebDIV patch breaks your LDAP authentication.
So users can't log in. The entire business grinds to a halt.
Exactly. And now you're facing a traditional rollback, which is measured in hours, and it's actively crippling your business.
Right. A traditional rollback isn't just a single command. You're manually restoring files, reverting settings, maybe even running database rollbacks.
It's complex. It's not atomic, and it takes 4, 6, maybe even 8 hours. The financial cost of that in lost revenue and brand damage is astronomical.
And blue-green deployment is the radical answer to that whole mess.
It takes that 6-hour catastrophe and it turns it into a 30-second decision.
So introduce the concept. It's basically taking infrastructure redundancy to an architectural level.
It is. It's architectural redundancy with a very specific operational purpose. You maintain 2 full, identical production environments. Let's call them blue and green.
And only one is live at any given time.
Right. Let's say blue is active, serving 100% of your user traffic. Green is the completely isolated standby environment. All change patches, software releases, config updates, it goes to green first.
So you can test it in isolation.
Test it, verify it, and only when you're 100% confident do you use a load balancer to shift traffic over to green. And if green fails at any point, you instantly revert all traffic back to the working blue environment.
Okay, but let me bring up the challenge here. This sounds expensive. You're talking about doubling your infrastructure cost. How do you justify that kind of capital expenditure just for faster rollbacks?
That's a very real and important question. But the justification isn't based on the cost of the hardware. It's based on the cost of the downtime and the massive reduction in risk.
So you're not comparing server costs. You're comparing a server cost to a multi-million-dollar outage.
Exactly. Blue-green guarantees near zero impact for almost any operational failure. And in the cloud, you don't really have to double your cost indefinitely. Green only needs to be fully scaled up during the deployment cycle.
The rest of the time, it can be scaled down or even hibernated.
Right, which significantly reduces that standby cost. You're buying an insurance policy against catastrophic failure, not just paying a static expense.
That reframes the argument completely. And the real genius here isn't just having the 2 environments, it's how you switch the traffic.
That gradual switch is the secret sauce. An all-or-nothing cutover is still really risky.
So explain the mechanics of that gradual shift.
The system does it incrementally. You shift 10% of traffic, then you pause and run health checks. If they pass, you move to 25%, pause, run checks, and so on.
Up to 50%, 75%, 100%.
Exactly. But let's say at the 50% checkpoint, your performance metrics start to tank. The system detects that failure.
And it triggers an emergency rollback.
An immediate automated rollback. It sends 100% of the traffic straight back to the original known good blue environment.
So the blast radius is controlled, only half your users were affected, and only for the few seconds it took to detect the failure.
That's the core value. The failure exposure is minimized to a fraction of your users for a fraction of a minute. But this whole system relies entirely on how good your health checks are.
A simple ping test isn't going to cut it.
A ping test is worthless here. You need deep functional validation.
Okay, let's detail the 4 non-negotiable checks that our sources say you need to define true application health.
First, you start with the obvious, but you have to do it. Network connectivity. This is just a basic reachability check. It catches simple things like firewall misconfigurations or a server that failed to come back online after a reboot.
Second, you have to check the application process itself.
Application health. This means hitting a specific internal endpoint, usually health or status, and you need to get an HTTP 200 OK response. This proves the application actually started correctly and loaded its configuration.
So it catches initialization failures or missing dependencies?
Right. Third, you check its external dependencies. Most importantly, the database.
Database connectivity. And this has to be more than just checking if the port is open, right?
Much more. You have to perform a simple, low-cost query, like select one. This validates the entire connection path, the network, the credentials, the database connection pool. It catches all sorts of complex issues.
And finally, the ultimate test of function.
Authentication service. This is absolutely non-negotiable for any system with user accounts. You have to use a service account to attempt an actual login.
Because patches can so easily break things like SSO or LDAP integration.
They do all the time. If this check fails, your application is functionally dead no matter how good everything else looks. These 4 checks run automatically and repeatedly are what give you the confidence to switch.
The automation and coordination here must be intense. Let's walk through the 5-phase automated pipeline that brings this whole concept to life.
Right. There's an environment manager orchestrating all of this. Phase 1 is pre-flight checks. This is like the air traffic controller clearing the runway.
So before you do anything, you check for disk space, memory.
Disk space, memory, making sure prerequisite services are running. And crucially, you verify that a recent successful backup of the live blue environment has been completed. If anything fails here, the whole process stops.
Once that's cleared, the changes only go to the standby environment.
Phase 2, patch deployment. The manager marks the green environment as updating, and applies the patches. It integrates with your update systems and checks the logs for success on every single server.
Then in phase 3, you prove the application still works.
Phase 3. Automated testing. The manager runs the full test suite against the patched green environment. Smoke tests, integration tests, business logic tests. And you have to have an enforced timeout.
Like 30 minutes. If it's not done by then, it fails.
It fails. The integrity of that test suite is your first line of defense against breaking something.
And phase 4 is what catches the silent killer. The patch that works, but slowly grinds the system to a halt.
The performance killer. Phase 4. Performance validation. Manual testing almost never catches this. The manager compares key metrics from green response times, throughput, CPU, against the live baseline from blue.
And if performance degrades by more than a certain threshold, say 5 or 10%,
the deployment fails. This phase is what catches those subtle memory leaks or inefficient database queries that would otherwise turn into a nightmare hours after you've gone home.
It prevents a successful deployment that's actually an operational disaster waiting to happen.
Right.
And then finally, if everything passes.
Phase 5. The traffic switch. The gradual checkpointed shift begins, 10%, 25%, with health checks at every step. If they all pass up to 100%, green is now active, blue becomes a new standby, and you're done.
And if any check fails during that switch,
the emergency rollback is triggered, guaranteed by the architecture. All traffic goes straight back to blue, instantly.
The sense of relief this must give to an operations team is just, it's hard to overstate. That high-stress, all-hands-on-deck maintenance window is just gone.
It's gone. Patch management becomes boring. It becomes predictable. And it becomes fundamentally safe. You're not managing a catastrophic failure anymore. You're managing an isolated test failure with zero user impact.
Blue-green really masters the operation of change. But we still need to have confidence in the thing we're deploying in the first place, that explicit verifiable trust.
And that takes us out of the operations center and straight into the development pipeline. It's time to shift left.
Right. If we just relied on blue-green, we'd still be implicitly trusting that the code getting pushed to that green environment was, clean and authorized.
Shifting left is this conceptual move. It's about applying security controls and testing as early as you possibly can in the software development lifecycle.
And the really profound goal here is to replace that implicit trust, that handshake, that verbal, yeah, it's good, with something explicit.
With explicit, verifiable digital trust.
We're essentially creating a digital paper trail where trust isn't just assumed, it's cryptographically proven every single step of the way.
Exactly. Our sources break this down into 5 stages where you accumulate this trust. It starts with the secured baseline and the source code itself.
Okay, so starting with the baseline, that means infrastructure as code, or IAC. Why is defining your servers and networks in Co rather than clicking around in a GUI a security issue?
Because it ensures repeatability and auditability. When your infrastructure is defined in code, it lives in a version control repository. It can be tested, linted, and reviewed, just like your application code.
So you're deploying from a known, secure blueprint every single time.
Every time. And it's the only way to reliably enforce that principle of least privilege across your entire fleet of servers.
And this IAC foundation is also your main weapon against that constant threat of configuration drift.
It's the existential threat to any long-lived infrastructure. That's when the actual state of a server deviates from what's defined in your code, usually because of some ad hoc manual change.
So the radical countermeasure here is to just limit the lifetime of your resources.
It sounds crazy, but yes. We start measuring server lifetimes in days or maybe weeks, and then we periodically just redeploy the entire thing from that clean ISC blueprint.
The concept of immutable infrastructure. You treat servers like cattle, not pets.
That's the classic analogy. If your server is short-lived, the window of opportunity for an attacker to introduce some persistent change or for configuration to drift is drastically reduced. You're always resetting to a known good state.
Okay, so that's the infrastructure. Moving up the stack to the source code phase, there's a huge proactive step we can take, and that's advocating for memory-safe languages.
This is one of the most dramatic recommendations, but the data backs it up.
You're talking about that statistic that something like 70% of vulnerabilities are memory safety issues.
Roughly 70% year after year. We're talking about buffer overflows, use after free bugs, the kinds of vulnerabilities that are notoriously hard to find, but are devastating when they're exploited.
So by using languages like Rust or Golang or even C# and Java,
which manage memory safely by design, you are mitigating a huge chunk of potential vulnerabilities right at the moment the code is written. You're eliminating the problem before it can even exist.
That is security baked in, not bolted on. So the code is written. How do we guarantee who wrote it?
You enforce commit authenticity. Every major source code repo supports digitally signing your commits with asymmetric cryptography.
So you can verify the identity of every single contributor.
And if an unsigned commit is ever attempted, which could be a source of malicious code injection, the pipeline just fails. It adds an immediate explicit layer of trust right at the source.
Okay, now we move to the artifact itself, before deployment. We have clean code, but we need to make sure the compiled artifact is immutable and minimal.
Immutability is the key word. Artifacts must be versioned, and they must never change. We have to get rid of risky snapshot builds where version labels get overwritten.
So the cryptographic hash, the digest of the artifact, has to be the exact same from testing all the way through to production.
Any change, no matter how small, invalidates that hash, and the whole process has to stop.
And the minimalist approach, this idea of using distroless images, that sounds a bit counterintuitive.
It's minimalist for maximum security. A distroless base image contains only your application and its direct runtime dependencies. It removes everything else.
No package managers, no config tools.
And critically, often no shell access. No bash, no ish. So if an attacker does compromise that container, what can they do? Their ability to explore the file system or download more tools is basically gone.
You're reducing the attack surface from hundreds of potential binaries down to just a handful.
It's security through severe reduction.
Once that minimal artifact is built, we have to scan it. And there are two types of scanning that are mandatory.
Right. First is the OS level vulnerability scanning. You're looking for known CVEs in the base image components. This has to happen the moment it's uploaded to your container registry.
And the results get tagged to that specific image digest.
Cryptographically linked. And if the image has a vulnerability that violates your policy, say any high-severity CVE, the pipeline fails. It can't proceed.
But that OS scan won't catch a vulnerable library you've packed inside your Java jar file.
Exactly. Which is why the second check, application dependency analysis, is also non-negotiable. You use tools like the OS dependency checker to find vulnerable libraries inside your application code.
So the two scans work together to give you a full picture.
A verifiable inventory of all your external vulnerabilities at both the platform and the application layer.
Okay, let's move to the deployed artifact phase. A big challenge here is managing secrets for different environments, dev, staging, prod, without changing the artifact. How do external secrets managers solve this?
They solve the coupling problem. Secrets have to be decoupled from the application and the environment. Your application code should be totally environment agnostic.
So instead of having dev.db.password in a config file, the application just asks for db.password.
Exactly. It asks a single secret name. And when it queries the external manager, like Vault or AWS Secrets Manager, the manager provides the right value based on the identity of the service that's asking.
So the application artifact stays identical across all environments.
It stays immutable.
Yeah.
And this hugely reduces the risk of secrets leaking in your source code. But the biggest security win is centralized auditing. Every single interaction with the secrets manager is logged. You get an invaluable forensic trail.
And then there's the benefit of isolated testing environments. Why is spinning up a temporary environment for a single feature branch better than using a shared dev or QA environment?
Because shared environments are messy. They accumulate historical cruft that makes testing unreliable. Ephemeral environments, which you create with IAC and then destroy immediately after use, give you a perfectly clean, isolated target for your security checks.
Like dynamic application security testing, or DAST.
Right. If DAST finds a flaw, you can instantly reproduce the exact vulnerable environment and the exact artifact version, test your fix in perfect isolation, and have high confidence before you merge. It removes all the noise.
Okay, we've shifted left. The artifact is built securely, it's scanned, it's tested. Now, how do we create the ultimate gate? How do we use all that accumulated trust to enforce that only this verified artifact can run in production?
And that's the final cutting-edge transition. We have to leverage that cryptographic trust at the moment of execution.
So all that trust we built up, passing the scan, completing the tests, getting QA sign-off, it's formally recorded using what are called attestations.
An attestation is just cryptographic evidence. It's a verifiable claim that a specific event for a specific artifact happened successfully.
So if the test suite passes, the system issues a kind of digital certificate of completion, and it's linked directly to the artifact's unique hash.
Precisely. And this whole system relies on two roles. signers, and attesters. The signer is the entity. It could be an automated scanner or a human QA manager that holds a private key. They use that key to sign the attestation evidence.
Which cryptographically guarantees that the claim is authentic.
And hasn't been tampered with. The attester is the service that acts as the gatekeeper. It uses the signer's public key to verify that the signature is legit and that the artifact hash matches the image you're trying to deploy.
So we're moving accountability from, did Bob sign off on this in the ticket, to, can we cryptographically prove Bob's private key signed this artifact?
It's verifiable, non-repudiable proof of compliance. And that proof is then enforced by a service like Google's binary authorization, which acts as that deploy time gatekeeper.
And binary authorization uses policy as code, PAC-C, at the cluster level. What kind of rules can you set up?
The PAC rules define the absolute, non-negotiable criteria for deployment. Your production policy might be extremely strict. It could require, say, 3 different attestations.
One for the build, one for the security scan, and one for management approval.
All signed by different, distinct signers. If your policy demands 3 attestations and the artifact only has 2, or one of them can't be verified, deployment is denied. Period. It's the final, immutable security barrier.
Let's talk about the failure modes for that. What happens if the security scanner service itself is down during a critical deployment?
This forces you to make a really important choice between 2 failure modes: fail open or fail closed.
If you're set to fail open, you let the deployment go through anyway.
Right. You're basically saying that service availability at that moment is more important than the security validation.
Which seems incredibly risky for a production system.
It is, which is why for any production system with sensitive data, the only real choice is to fail closed.
Meaning you actively deny the deployment.
You deny it. The logic is, if we cannot verify the required trust, we have to assume maximum risk and deny execution, even if it causes a temporary operational delay. You're prioritizing integrity over immediate availability in that specific failure case.
Okay, that secures the application from source code all the way to runtime. Let's circle back to the infrastructure it's running on. In Azure, for example, how do we make sure the VM itself hasn't been tampered with at the lowest level?
That's where Microsoft's trusted launch for Azure VMs comes in. It's designed to protect against those really nasty low-level threats like bootkits and rootkits. It makes sure the VM starts in a secure, measured, and verified state.
And it uses 2 core technologies to do that. The first one is Secure Boot.
Secure Boot is a standard UEFI feature that validates the integrity of the entire boot sequence. It makes sure that only trusted OS loaders and kernels are allowed to run. It stops malicious code from hijacking the system before the OS even loads.
And the second piece is the VTPM.
The VTPM, the Virtual Trusted Platform Module. This is the critical part. It's a dedicated, secure processor that stores cryptographic keys and measurements. During the boot process, the VTPM takes a measurement, a hash, of all the boot components.
And if those measurements don't match the expected baseline?
It's a sign of tampering. The VM can refuse to boot or at least alert administrators that the trust chain has been broken. It's the immutable hardware anchor for the VM's identity.
And the fact that Microsoft enabled in-place upgrades for this is a huge win for adoption, isn't it?
It's a massive operational boost. Normally, adding a security feature this deep would mean a complex, risky redeployment. Being able to do an in-place upgrade means organizations can get these benefits without downtime. It removes a huge barrier.
So we have verified infrastructure, we have cryptographically verified applications. The final piece of the puzzle is access control. We hear zero trust all the time, but the traditional way of doing it, even with the big PAM system or a bastion host, has a fundamental flaw.
The flaw is centralizing trust. In a traditional PAM model, you get rid of user passwords, which is great, but you replace them with a single, super privileged vault that holds the keys to everything.
You've just created the ultimate single point of compromise.
The juiciest target an attacker could possibly imagine. And we've seen it in major breaches. Colonial Pipeline, Uber, Medibank. Attackers go after the access manager itself because if they compromise that one thing, they get the keys to the entire kingdom.
So if we can't trust the centralized vault, how do we manage access at all?
We have to move to a decentralized model of assurance. Something like the multi-root trustless access protocol, or MRTAP, which systems like Bastion Zero have pioneered.
Multi-root. What are the 2 independent roots of trust here?
The first root is your organization's existing identity provider, your SSO system. That verifies the user's corporate identity. The second route is an independent multi-factor authentication, or MFA, to the Bastion Zero cloud service itself.
And neither one can grant access on its own.
Critically, no. Neither route has the unilateral authority to compromise the target. Even if an attacker completely compromises your corporate SSO, they still don't have that second independent MFA token, and vice versa. It minimizes trust in any single authority.
And this approach completely eliminates the need to store or distribute any secrets to the individual servers.
It's truly passwordless and credentialless. The cryptographic protocols handle the secure session under the hood. For admins, it's a huge productivity win. No more key rotation, no more secret distribution, and for security, you've eliminated an entire class of risk.
This system also uses something called the phone home architecture. How does that simplify network security?
It completely flips the connection model. Traditional systems need you to open inbound firewall ports or set up VPNs so users can reach the servers.
With the phone home architecture, the servers themselves initiate the connection.
The targets, the servers, the Kubernetes clusters. They initiate a secure outbound connection to the Bastion Zero cloud service, and the service then mediates user access across that tunnel.
So you can close all of your inbound ports.
All of them. There's nothing for malware to scan, nothing for an attacker to discover. It removes the complexity and the risk of managing VPNs and Bastion hosts. Your attack surface just shrinks dramatically.
Finally, let's talk about auditing. It's often the weakest link. How does this kind of system handle auditing in a really complex environment like Kubernetes?
Kubernetes auditing is a nightmare. A user types one simple command, and it generates dozens of cryptic API calls in the logs. You lose the user's intent.
So tools like Zycube solve this by wrapping the standard command line interface.
Exactly. It captures the user's original English text command, the exact thing they typed into their terminal, and it associates that one command with all the resulting API calls in the audit logs.
It bridges the identity gap.
It gives you a highly granular, identity-aware audit trail that shows both intent and outcome. It makes incident response infinitely more effective.
And that brings us to the end of our deep dive. We've traced the entire stack from the OS kernel all the way up to decentralized access control.
It's been quite a journey.
So what does this all mean?
Well, we've traced a really powerful logical arc today. We started with the basics, the reactive hardening of a server OS with NIST principles.
Then we engineered this operational safety net with blue-green deployment to get rid of the fear of downtime.
From there, we moved into building a proactive, cryptographically verified software supply chain using shifting left and binary authorization.
And we wrapped it all up with this next-generation access model that just refuses to trust any single authority, whether it's a human or a machine.
The knowledge we've gone through today really provides three crucial, actionable takeaways for you, the learner, as you navigate system security.
Oh, let's hear them.
First, the goal isn't just to minimize downtime. The goal should be zero downtime, even for the most critical patches. And that's achievable through these guaranteed, phased, auto-validated deployments, where the architectural choice of blue-green ensures that any failure is measured in seconds, not hours.
Second, trust in your software supply chain has to be explicit. It has to be purely digital. We have to move past human code review as the final gate.
Security demands cryptographic evidence attestations that are rigidly enforced by deploy time policies like fail-to-closed binary authorization.
And third,
Critical infrastructure access demands multi-root trust. Centralizing all your privileged credentials in one place is a fatal design flaw. The future of access is decentralized, it's credentialless, and it requires two independent keys for every single login.
So we've built this completely verified, cryptographically secured pipeline, pushing code to a trusted infrastructure, and we're accessing it with a trustless mechanism. It sounds like we've solved every security problem.
We've removed almost every opportunity for accidental human error or external malicious tampering from the deployment and access workflows. We really have.
Which brings up a final important question for you to think about. If we can cryptographically prove our code hasn't been tampered with, and we can enforce access using two independent keys, what is the last security vulnerability? The one that remains completely invisible to all of these automated digital trust systems.
Where does the vulnerability still live?
Is it the fundamental flaw in the original design of the business logic? A vulnerability that was baked into the application's requirements document itself long before a single line of code was ever written.
A provocative thought. And one that underscores that even in a world secured by cryptography, human critical thinking is still absolutely essential. Thank you for joining us on the Deep Dive.
We hope you walk away feeling thoroughly well-informed and ready to implement true operational resilience. See you next time.